Okay, lots of announcements to cover. The first of which is, if you haven't already, please download and install Bentley StormCAD. I think I've emailed you the links to that before. They're posted in the Blackboard, the links. And so to do that, you'll have to create an account with Bentley Education if you haven't already, and then you can download the installation files, and then you have to log on to the select server in order to get the program to run. That's their license server that runs down in the system tray. If you have any trouble accessing the installation files, let me know, and I can help you out. So design project number 1 is due before 11:59 p.m. on Monday. I've got some good questions about the Flume, and so I wanted to go over some clarifying information regarding the partial Flume design today. Monday's class will be posted online because of the eclipse. I want you to go outside and stare at the sun for an hour rather than be in class. Did anybody here get that email that Cabell County Schools sent out? It's like they're really going to be aggressive with the kids, not letting them look up, not going outside during the eclipse. They don't want any liability of some kid going blind by staring at the sun too much. So it's kind of funny. So Monday's class, I'll email you the link to that when the video is posted on YouTube. I'll also post the link in Blackboard. And design project number 2 will be your last submittal item of the semester, and that'll be due before 11:59 on Friday the 19th, which is the last day of classes. So I haven't prepared that project yet, but I will. I've got an idea of what I'm going to have you do. It's going to relate to what we're getting into now, which is some of the principles of designing storm sewers. And then finally, our final exam is the very last day of finals and the very last exam period of finals. So we're going to leave the best for last, have your final exam in this class Friday at 12:45. So those are the announcements. Looking to the end. Anybody have questions before we talk about the partial Flume? Okay, so this is a hint on Design Project 1. On Design Project 1, the first part of it, I've asked you to size the partial Flume that you'd need for a certain watershed so that it can pass the 2-year storm without submergence. So when you design a Flume, what that basically means is you delineate the watershed, you do the hydrologic analysis, and you find a flow rate Q. Has anybody already found the flow rate for the watershed? So a handful of you have already found the Q. So if you know the flow rate, this table of equations tells you like what throat width is appropriate for a typical flow rate. So let's say maybe that you found the flow rate was 5 cubic meters per second. So that would tell you that the throat width for 5 cubic meters per second should use this equation, which is valid for ranges of 30 centimeters in width up to 2.4 meters in width. And so you need to pick a width and then find out what would be the H sub A for that flow rate and the width that you've selected. So that's just analysis. Now, in the instructions, I tell you to design it so that you avoid submergence. Now, submergence is measured by H sub B, and that's not one of the parameters that goes into your equation. So the way that you know how deep H sub B is allowed to get is you calculate H sub A from the formula, and then you'll remember that there are these submergence criteria tables. Let me go back to where we were talking about flumes before. So here's the table of submergence criteria. So if you're using 30 centimeter to 2.4 meter flume, then the ratio, the maximum allowed H sub B is 70% of H sub A. Okay, so you just say, all right, so that's the deepest H sub B is allowed for the flume that you've just designed. By design, I mean you've selected the width and calculated the H sub A. So calculated H sub A, find out what's the maximum H sub B. Now what determines the H sub B depth is the tailwater. And if the channel downstream is not able to convey much flow, like if it's relatively flat, or if it's very, very rough, or if the channel is narrow, then you would have a poor flow capacity downstream and a large depth. If the depth in the tailwater is too high, that will drown your hydraulic jump in the flume and exceed the allowable submergence. So what I'd like you to do is just analyze the tailwater. And this is something that you've also done recently with the culverts. You know, there's that tailwater calculator within HY8. And so you don't need to use HY8. You can just use Manning's equation. Use Manning's equation and let the normal depth be equal to that maximum allowable H sub B, which you determined from the submergence table. So 70% of H sub A, for example. And then find out how wide would the channel need to be for a typical N value from the table that's on the handout. So the table I gave you said, like, for example, earth-lined channel would have an N value of 0.02. So if you use that earth-lined channel 0.02 and the slope of the channel you can actually get from WMS, it will tell you as one of the parameters that it estimates is what's the slope, not of the basin, not of the ground slope, but the slope of the channel, the main stream that's carrying flow. So you get the channel slope, and just use Manning's equation to find out how wide would that channel need to be to avoid submergence. And then, like if it says the channel needs to be 100 meters wide to avoid submergence, that's probably not going to happen for this little crossing that we're analyzing out in Cabell County. But if it says the channel needs to be a meter wide or wider to avoid submergence, then we're probably good and we're going to avoid submergence. So what I'm asking you to do is just consider the effect of the stream that's beyond the flume, because H sub B is governed by the tailwater depth. Any questions about that? Wyatt, does that answer the question that you had? All right, good. Lucky for you guys, Wyatt's working ahead, so you're getting hints because he's getting an early start on the project. Okay, well, let's talk about the rational method. You know, we briefly dipped our toe into the rational method a few weeks ago because some people needed to hear about it for the senior projects. But let's revisit that. You may have noticed in a lot of towns, including Huntington, I've noticed some of the inlets in Huntington have like painted symbols in front of them, just to remind you that when you put something into a storm drain, that it's eventually going to get out to a creek where there's fish. And so they're warning you, for example, don't dump used oil into a storm drain, or antifreeze is something that they sometimes get problems with, people dumping used auto chemicals into these drains. And you shouldn't do it because storm drains will get back into the natural environment. And sometimes water from storm sewers goes to ponds. Some ponds can just be like an earth-lined area that doesn't have any development on it, a low point in a park, for example, or off to the side of a commercial development. Sometimes they can be really nicely landscaped, and it can be kind of a design feature. But we're going to look at the sizing of ponds next week. But today we're going to look at the issue of what flow rate would be coming into a pond given a certain storm size. So we're moving on to the idea of stormwater management. Water is both a resource, but it's also sometimes, depending on how much of it you got, sometimes water is just this nuisance that has to be disposed of. And so people in arid climates would cringe to hear us talking about water as just this nuisance thing that's causing problems for us, but you know, it's going to flood and cause damage unless we manage it in a sensible way. So drainage systems help us to do that, and they preserve safety, because if you have too much water in the road, then as people are driving along in their vehicles, if just one side of the car's wheels are in water and the other side aren't, you've probably felt it before, where it'll jerk your car to the right if your right wheels are in the tire and have more drag than the left wheels, which aren't in the water. So it's a safety issue, it's a pavement longevity issue, keeping water out of the streets. We manage stormwater through drainage systems to make sure that gutters don't have too much flow going in them, and that the velocity of water in a gutter isn't so fast that it could knock children down And that's an issue in really steep towns like San Francisco, for example. When they have a rainstorm, the water in the gutters alongside the road can be moving really fast, and that itself could be a danger. We use drainage systems to convey runoff into either natural receiving bodies like creeks and rivers or lakes, and then sometimes to manage man-made drainage systems as well. We can put filters or settling basins to try and remove sediment or heavy materials like lead, heavy metals, or trying to strain out oils that float to the surface of stormwater. Because a lot of stormwater coming off of roads has the same chemicals that vehicles are associated with, like gasoline and grease and oil. So roadway surfaces are coated with all of these dirty chemicals and grit, and when it rains, all of those things get washed into our stormwater management system, and so we have to engineer ways to remove those pollutants before the water gets into the natural waterways. And if possible, what we look to do is when we're sizing a detention pond to serve as a temporary flow equalization system, we would like for it to be useful for multiple reasons besides just as water storage. Because they won't have water in a dry pond. It'll only have water occasionally, a couple times per year. And so it's nice if we can design it to be like a park or a recreational field. So I think I previously showed you this figure that was looking at a section of Huntington that has both a standalone separate storm sewer, and then it has a wastewater collection system that also receives stormwater. And so a combined system is one where homes are discharging wastewater from flushing the toilets, from the flow from their sinks, but then the stormwater gets into the pipe when they have roof drains, which are connected to the sewer, or foundation drains, or sometimes they'll have catch basins in a neighborhood, which are inlets that are trying to capture stormwater flow off the street. And so a combined sewer would have both a base flow that's wastewater, but then also flows which vary quite a lot during storm events. So some of the things that we look for when we do a design and we're trying to manage stormwater is understanding what local design standards, and if a city has regulations related to the allowable flow velocities or how much capacity you have to put into a sewer. There are a lot of only locally applicable regulations that say, how much flow capacity you have to have per square acre of land that's being developed, or how much flow capacity per 100 residents. And so you have to know those local design standards, and also having topographic data will allow you to know the slope of the land and how water's going to move around over the surface when it rains. Obviously, you'd want to have data related to where the existing pipes in the network are. If you're going to be putting new pipes in or trying to tie in to the existing pipes, then you don't want to overload the existing infrastructure. And so having all that existing data is really critical. There can be power lines that are also buried underground, internet, gas, and so all of the utilities you'd need to know about to try and avoid them when you lay out a new sewer line that's going in. You'd want to have the information related to the street profiles and grades if you're expected to put in curb and gutter and inlets and manholes, then knowing where the new area development roadway network is. And then there are some soils which can be corrosive to certain types of pipe. And so whether you use concrete pipe or plastic pipe, or in some rare cases they'd use metal pipe for a stormwater drain. But you need to have soil data in case there are any kind of corrosion concerns having to do with the materials that you're using with your network. Knowing the water table helps you to know whether the risk of buoyancy of the pipe is a problem, because some pipes which are relatively light, like a plastic pipe, if the water table is above the pipe, then there can be a buoyant force that pushes the pipe up, and in some rare cases the pipe can actually break through the the pavement that's over the top of it, if the water table is high enough and the diameter of the pipe is high enough, the buoyant force may exceed the weight of the soil on top of the pipe. So knowing the water table can be another factor that you use in determining whether you're going for a heavy pipe material where buoyancy would be less of a concern, like a concrete pipe. Rainfall data for the project area, pipe property. So all of this would be kind of the baseline of information that we'd want to collect before we do a design and figure out what type of pipe we're going to have for conveying stormwater, where it should be located, the required diameter, how frequently spaced inlets are. So some of the things that we'll assume for stormwater collection networks is just that water is flowing by gravity. Hopefully we can achieve that, because when you put in a pump station for stormwater or for sewage, it's really expensive to lift water and to pump it from one place to another. Electricity costs already account for a huge percentage of the cost of treating wastewater, and that's even before you take into account the electricity that could be consumed when you're pumping water from place to place. So ideally what you want to do is design your flow so that it's going towards the lowest part in the network, and you don't have to put in pumps to move the water around. Typically, stormwater is moved through circular pipes, which are commercially available, and so that may limit the variety of sizes that you have. So there could be a 15-inch pipe, a 12-inch pipe, an 18-inch pipe, but maybe there wouldn't be a 14-inch pipe or a 13-inch pipe. So you just have to be familiar with what you can get your hands on in the area where a project will be done. What we do for optimization's sake is go for the smallest pipe diameter that we can, that's going to be acceptable, that will convey the flow. And it's a risky thing where in your mind you may think, if we make the pipe larger, then that builds in more of a safety factor. And that's true from one sense, but there's a risk that if you have an unnecessarily large pipe, that there can be friction involved, which causes a lack of cleansing of the pipe. And let me just on the board illustrate that if you have a relatively small diameter pipe, when the water's flowing through there, it would be most of the way full. And during the low part of the day, like at night, when people aren't flushing their toilets and there's not a storm event, maybe the water levels would be lower, but still there would be enough velocity to prevent sedimentation. So both stormwater and wastewater has solids that can settle to the bottom of the pipe potentially. And the problem with a large pipe, if you're thinking I'm going to do everybody a favor, put in all this extra capacity, at night when the flow is low, it would be very shallow. And what you know about shallow flows is if there's a long wetted perimeter, then it's this wetted perimeter that's exerting a shear stress on the water and causing the velocity to be low. So if you've got a small pipe and at night the depth is relatively high, then the velocity would be high. Or we could say high enough, above the minimum. But if you have a big pipe, then you've got a big wetted perimeter, you have lots of resistance, and a low velocity. And the velocity may be too low. The minimum velocity that's in place exists to prevent sedimentation and to promote self-cleansing. So smallest pipe diameter is both about saving money and also improving the overall performance of the pipe network. We have to have some minimum cover over the top of the pipe to help distribute loads and also to avoid, depending on the climate of the area that you're in, if you bury the pipe deep enough, then the water will stay liquid even during the winter time, when otherwise it might freeze if it was buried too shallow. So minimum velocity and sediment deposition is an issue that we're going to want to keep an eye on, the flow being too low, but also if the flow velocity in the pipe is too high, and that causes erosion of the pipe and scour. One of the principles that we employ in design is that in a dendritic pipe network, which is all funneling down to one central location where the flow is collected and discharged to a stream, or if it's being collected and treated at a treatment plant, the pipes only get progressively larger to prevent clogging. So you wouldn't have a big pipe connected to a smaller pipe and flow going from the large pipe to the smaller pipe, because then that's a risk of it becoming clogged. So just for that reason alone, even if it's not needed from the perspective of capacity, like if you had a really steep section of ground, even if you could get away with a 12-inch pipe, if there was a 15-inch pipe prior to that steep section of ground, you'd stick with the 15-inch diameter. Even though it may not be needed hydraulically, we don't have smaller sections of pipes because they can get clogged. Okay, so here's a diagram where I wanted to show and discuss a few key points related to infiltration and inflow. Inflow and infiltration are considered kind of parasitic flows that get into a pipe network and take up capacity. Those are flows that shouldn't be there. And so it can be, for example, in an area that has both a storm sewer, which is separate from the sanitary sewer, then any kind of crack in the sanitary sewer, so a crack in the pipe, or if the roots of a tree have punctured the pipe and they're allowing groundwater to get in, then that's going to be adding to the flow that has to be treated. And sewage treatment is mainly tied to the volume that's being treated, and less so the cost of it is related to the strength of the sewage, meaning the concentration of pollutants like BOD. And so you really want to reduce how much water is getting into the sewage treatment that doesn't need to be there. So you wouldn't want drains from the roof connected to your sewer system, because that's adding to the volume that needs to be collected and treated, and it's very costly. So this house on the left is doing all of the wrong things, because it's got a foundation drain and a roof drain going to the sewer pipe, whereas the house on the right is doing all of the correct things, because they have the roof drain and foundation drain going to the storm sewer and bypassing the sanitary sewer. So storm sewers can, if the water's clean enough, just discharge directly to a creek or a river or a lake without needing the same kind of extensive treatment that occurs for a sewage treatment plant. So another thing I wanted to point out in this figure is, see the catch basins that exist here in the gutter? How frequently we need to space those catch basins depends on the slope of the ground, how wide the lanes are, and the capture efficiency of the catch basin. So when we do really detailed calculations of the hydraulics in an urban environment, we're not just figuring out how big the pipe should be. That's what we're going to focus on today. And next week, when we start using StormCAD software, the only part of that we're going to do is sizing the storm sewer pipe, so figuring out the diameter. But there is a component of StormCAD that will also allow you to analyze the flow in the gutter. And so the gutter is just like an open channel. So you can use Manning's equation to find out how deep is the water in the gutter, and what is the velocity of the water in the gutter, and then the capture efficiency as the water flows over the surface of a catch basin, what percentage of the water is retained and goes into the storm sewer. So it's both closed conduit flow in the storm sewer, but also open channel flow in the gutter. An important part of managing stormwater infrastructure is doing regular inspections. And they're getting these increasingly sophisticated drivable robots that will go down in the sewer. And so far, they're always monitored by a human at the surface, like who's watching a TV screen of the robot driving through the sewer. And what they're looking for is cracks in the pipe. They're looking for illegal connections where people have put a pipe that they're not paying a sewage fee for. They're looking for, what shouldn't be there, so that they can make repairs, or for violating people who are discharging to the sewer that shouldn't be. I think in the future, most likely, they're going to have these systems become automated. And so they'd use sort of image evaluation and AI technologies to send sewer robot inspection robots down into the sewer, and then they wouldn't have to be monitored in real time, but maybe if the software detected an anomaly, then a technician would look at the pictures just at the problem sites rather than the whole time. The issue is that just knowing where the problem is doesn't always allow you to fix the problem. This is a figure that I found online that is illustrating the amount of spending on water and sewer systems across the United States. And a little bit of history is that back in the 40s and 50s, there were a lot of federal grants that allowed communities to put in sewer systems and storm sewers that previously didn't have networks. There was a really good program of federal subsidies to try and encourage people to improve like the quality of rivers, like water from sewers was getting into rivers, and it was causing much higher pollution than could be tolerated. And so the federal government put these subsidies into building wastewater treatment plants and collection networks, but then it was going to be on the local governments to maintain and pay for the upkeep of those networks. And so over the years, as these pipes, sewers have become more broken down and older, you can see that the local governments are spending more and more on their water systems and their sewer systems. And here in Huntington, it's really a huge burden, where a lot of the flooding that we have routinely along Fifth Avenue, on Hal Greer, and under the railroad tracks. I don't know, did anybody try going under the tracks when did we get all that rain? Was it Tuesday? It was closed, right? Hal Greer was closed under the tracks on Tuesday because it just gets flooded down there. The city of Huntington doesn't have enough money to rehabilitate all of the pipes that need to be fixed. There's just not enough money in the state of West Virginia to fix all of the drainage, sewer, and stormwater issues that need to be fixed. And so it is important to inspect, because the inspections allow us to prioritize spending on the places where it can be the most effective. But I just wanted to point out that this is more than just an engineering problem. It's also a political problem and an economic problem, maintaining this infrastructure. And so we have to think about that from an engineering perspective. Like when we are developing new land and we're putting in infrastructure, the client has to be guided in how much to set aside for the future maintenance of roads and sewer networks. So some of the numerical limits that we're going to be applying when we do design with StormCAD is that there should be a minimum velocity associated with self-cleansing and a maximum velocity that's allowable related to scour and damage of the pipe. There's a maximum spacing of manholes that you'd want to have in place because you need access to the sewer at regular intervals for inspection and cleaning. Because not all sewers will be perfectly self-cleansing, and so they sometimes need to flush the accumulated sediment out of the bottom of the sewer. And so a spacing of 400 to 600 feet is appropriate to make sure that you can get access to the cleaning and inspection. Most sewers would have a minimum pipe size, which even if it's not needed hydraulically, a 12-inch minimum size would allow you to get camera systems down inside to inspect them. And then the other thing I wanted to point out here is that surcharge is pressurized flow in a network that is intended to flow open channel and under gravity. And so if we have a pipe that is most of the way full, so it's nearly to the top, it actually has more flow capacity when it's most of the way full than if it's all the way full. Because right now, if you look at the ratio of the cross-sectional area of the flow, and then the wetted perimeter around the length, the cross-sectional area is allowing flow, the wetted perimeter is resisting it. So if you make it just a little bit deeper, you're not getting that much additional flow area, but you are picking up some additional wetted perimeter. So if the water is all the way to the top, you've lost a little bit of your capacity compared to the maximum. And then if there's now pressure inside the network, it can begin to leak out of the joints where the pipe comes together. And there could be low points in the network where the water rises and it actually discharges out of the drainage system. So if any of you have ever driven on Route 60 by Ollie's, and you know, like Academy Sports on Route 60, have you ever noticed there's a smell there, a lingering smell? Like it smells like sewage over there, and it's not just because it's like, you know, a bad steakhouse or whatever that's over there. They have wastewater that comes out of the sewer because it's at a low point in the network, and so consistently in wet weather, I don't know if it's a combined sewer there or if it's just that there's a lot of infiltration and inflow into the storm sewer, but sewage is getting out there, and you can smell it because they have pressurized surcharged pipes where the amount of water in the pipe is so high and the pressure of it that it's actually coming out of the inlet covers and grates and so on. So the rational method says if we know the area in question that we want to provide service to, then there's going to be a certain amount of rainfall intensity for a storm that we're interested in. So we can get that data from the precipitation data frequency server, the rainfall intensity for a return period of, say, 5 years or 2 years. Whatever we want to analyze, we can get the rainfall intensity that's associated with the return period at also the time of concentration. Remember, the time of concentration is how long it takes for the water to travel from one edge of the network to the collection point that we're interested in. So we could use the Kirby method, the Kirpich method, NRCS. There's all these different equations depending on what data we've got available and the level of precision that we require in estimating the travel time. And so when we know the time of concentration and the intensity, then we will assess the ratio of runoff to the amount of rain that's coming and determine a C value. So we've talked about this before and how the peak runoff Q is equal to the intensity of the rainfall multiplied by the area multiplied by the C value. So Q equals CIA. And what's the units coincidence? Do you remember the coincidence of units, like talking about the units of the left-hand side of the equation and the units of the right-hand side equation for traditional British gravitational units?
With the area in acres, it'll give you a Q per second.
Acres, cubic feet per second.
And then inches per hour.
Inches per hour. Good. That's right. And of course, C is unitless. So it's good you remember that. It turns out that it's actually, you know, there's a units conversion factor of 1.008. If we want to make it perfectly so that it's cubic feet per second on the left-hand side, and the units that we've used on the right-hand side, inches per hour for intensity, acres for area. But 1.008, we don't usually know the C value with enough precision to even bother with that correction factor. So we'll just leave it as 1. Of course, you could also, if you wanted to, if you want to be a stickler about it, you could also have your area be area in square feet. You could have your area be feet square, and your inches hour, you could have inches per, you do feet per hour. Feet per hour, and then what you'd get out of Q would be cubic feet per hour, and then from that you could convert it to cubic feet per second by dividing by 3600. So in SI units, what we'll usually do is express the acres in hectares, convert it to square meters, have intensity reported to us in millimeters per hour, and we could convert that to meters per hour. And then from that we get meters per hour, and we can convert it to cubic meters per second. So we've seen this slide before when we jumped ahead in that prior lecture. We've seen the C values for different types of materials, how, for example, if you've got a grass lawn on a flat area and you're estimating the runoff from a 2-year storm, then we'd have the C value being 0.3. No, for grass in, let's say, good condition, then it would be 0.21. So only 21% of the rain would run off, and the rest of it, 79%, would infiltrate or be retained on the surface. And then, of course, as the return period increases, so does the C value, meaning that more is going to run off. A greater fraction of the flow is running off for these large storms that have more volume to them. And then urban areas which are developed, like impervious surfaces like concrete or asphalt surfaces, have much higher C values, which also increase in value as the return period goes up. So we've seen these C values before, and we're going to skip over this example. This is just the same kind of thing where if you've got a certain amount of it that's parking, a certain amount of it's lawn, certain fraction is rail yard and single family housing, then what we would do is calculate a composite C value, composite runoff coefficient, like an area weighted runoff coefficient. So you can see here, if we knew a certain amount of area is each one of these, then we calculate a weighted C value based on not only the C value of the individual constituents, but their area. And then in this problem, we were told what the rainfall intensity is, 95 millimeters per hour. And then this area of the overall watershed of 38 hectares, we could multiply that by, there's 10,000 square meters in a hectare. So Q equals CIA, this would give us the peak runoff from a certain area. You've seen that before. What I want to save time for is this example. It's an example where I've placed a spreadsheet onto Blackboard, and we're going to work through it together. It's calculations that could be done by hand, but depending on how complicated a network is, it may just be a nuisance for us to do page after page of hand calculations. And so if we have a pipe network with dozens of pipes, then setting up a spreadsheet could allow us to copy and paste formulas and save a little bit of time as we size the pipe. So we're going to do design with this spreadsheet. And by design, there's a lot of parameters we can't control in a drainage network. Like the slope of the pipe is not something that we generally have engineering control over, because we have to have the slope of the pipe match the slope of the ground, typically. You couldn't have the slope of the pipe be really steep if you're in an area that has flat ground, because then the pipe is going to be so deep that you'd have to pump the water back up again. We won't have engineering control over the area that's being developed. That's just, if someone's developing a commercial area, or if it's an existing part of town that we're finally putting in a drainage network for. The areas are a given. The C values are things that we'll look up based on the characteristics of the neighborhood and the tables we just saw. So when we do rational method analysis to design a storm sewer, we're just basically finding out what's the size that's appropriate. So we're going to go through this template file that I put onto Blackboard, and we're going to see we've got two catchments. We've got this first catchment with an area of 1.5 acres, and the known time of concentration is 10 minutes. And so that just means it takes 10 minutes for the water to flow from the furthest most edge to the inlet. That's the travel time over the surface. And then for the second area, you can see it's bigger, 3.2 acres. It takes 30 minutes for all areas of that watershed to be contributing to flow at catch basin 2. So we want to find out how big should pipe A be, and how large should pipe B be. Okay, so here's the steps we're going to go through. Here's a precipitation data frequency server that I think is at the bottom of the file that I've given you for the location we're interested in. I don't know why that's missing. Is yours got an empty spot? Oh, there it is. I don't know. Maybe it's just the monitor being weird for a bit. Okay, so we're doing the 10-year storm. That's the setup here. We want to size the pipes so that they can carry the flow from the 10-year storm. We're going to calculate the flow rates that should be accommodated with Q equals CIA. And then Manning's equation has been rearranged to solve in terms of the diameter that's required. So D sub R is just saying, if you know the slope and you know the flow rate and the roughness of the pipe is specifying N, then the D sub R will tell you what diameter is needed. And then you can see here the conversion factors of whether you're in BG units or SI units. So we'll use this D sub R formula. Okay, so here's the template file. Have you found that online? Have you got it? Okay, let's start with pipe A. Pipe A, which is this first one, which is carrying water from catch basin 1 to catch basin 2. So the question is, how big should it be? Let's put in the parameters that we know about pipe A. Its length is 450 feet. The slope is given in the problem statement here in the diagram, 0.01. So it's a 1% slope, 0.01. The upstream junction is catch basin 1. The downstream junction is catch basin 2. We're just putting in what we know about this system. The area of the watershed that feeds water to the pipe A is 1.5 acres. So we're working in traditional units here. The problem statement says that this first watershed, the one on the left, has a C value of 0.75. Okay, so the C value is 0.75. Okay, now we're going to do our first calculation here. C times A. So it's the C value multiplied by the area, 1.13. This next column, you can see here I've explained what all these different columns mean and what you should do. So if you want to review this later, be sure to read through these definitions, and it'll help you to understand what we're doing in each cell. The sum of CA for a pipe that has no other pipes upstream of it. So pipe A doesn't have an upstream contributing pipe. It's just going to be the area and the C value of this first watershed. The sum of CA will be different for pipe B. But for this first one, we're just going to do the same as the previously calculated 1.13. The overland flow time was given as 10 minutes. That's how long it takes for the flow to go over the surface. And there's no upstream area before pipe A. So the cumulative upstream travel time is 0. And so therefore, the cumulative time of concentration is just the 10-minute overland flow time. So now the intensity that's associated with that, if we go down to the table, we're doing a 10-year storm, 10-minute time of concentration. So here's the 10-year storm. Here's 10-minute duration of the storm, and it says 5.23 inches per hour is the intensity. So let's put in the intensity of 5.23 inches per hour. And so Q sub P, the peak flow rate, is Q equals C times A times the intensity. So CA is the C value in the area. Intensity obviously is the rainfall depth and the time in hours. So that's going to be 5.88 CFS that's flowing through the pipe at the peak condition. So let's look at this formula for diameter required. I didn't intend to already have it in there, but it might be fortuitous based on how much time we've got left. So the formula that's in there for D sub R is this one. So let's just make sure it's using that M sub D, which should be for traditional units 2.16. So do I have the 2.16 factor in there? Yeah, I'm referring to this as the M sub D part of it. So that formula is calculating it needs 1.24 feet, which in inches, just multiply that by 12. So it says we need a 14.89 inch pipe. Well, they're not going to have pipe that's exactly that diameter. We have to round up to the nearest commercially available size, which would be a 15-inch pipe. You can find 15-inch pipes typically. So if we're going to actually use a 15-inch pipe, then the last part of this is to calculate what's going to be our flow velocity under peak conditions, and then how long does it take to flow through this pipe, which is 450 feet long. Okay, so you remember that we know that Q equals V times A. So the flow rate is velocity times area. So cubic feet per second is feet per second multiplied by the area in square feet. Or, if we want to know the velocity, we'll take the flow rate divided by the area. And for a circular pipe, area is pi d squared divided by 4. So that's what we're going to do in this cell, is the flow velocity is going to be the flow rate, so the peak flow rate, Q, and then we're going to divide it by the area of this 15-inch diameter pipe. So pi 3.14159 pi times d. So the diameter that's actually needed is cell R4. I can't click on it because my formula is centered. Now it's in the way. So R4 gives me the diameter in inches. I need to divide that by 12 to get feet. Pi d squared, now divided by 4. So that gives me the area in the denominator, and in the numerator is the flow rate. So the velocity of flow through that pipe is 4.79 feet per second. So how does that fit in with our minimum and maximum, like these typical values? Normally we'd want to see between 2 and 3 feet as the minimum velocity. We're above that, that's good. And we're below the maximum of, in a flexible pipe like a plastic pipe, you'd want to have maybe at a maximum 10 feet per second. Regardless of what this is made of, whether it's concrete or flexible pipe, we're good. So the flow time then would be the distance of 450 feet divided by the velocity. And so it's going to take, now I need to divide by 60 to get minutes. So that was seconds. Minutes is 1.56. So the formula is the distance of 450 feet divided by feet per second, and then divide by 60 to get the flow time in minutes. Okay, the last one I'm going to do real quick. It's 1:49, and I think that I may keep you 1 minute over today, if you will indulge me. Let me just show you what we do for pipe B. Pipe B was 600 feet in length. Its slope was 0.004. It goes from catch basin 2 to the outfall 1. The area of that watershed component is 3 acres. Let me just make sure. Was it 3 for that diagram? 3.2 acres. All right, so let me change this. 3.2 acres. The C value of that section was 0.55, and so C times A is 1.76, and then the sum of CA is both of the areas that are upstream are going to contribute flow to pipe B. So pipe B is carrying the water from this area and also the water from this area. So pipe B has 2 different amounts associated with it. The overland flow time was given as 30 minutes, and there was an upstream flow time of 1.56 plus the 10 minutes. So we take the bigger of these two, which is 30 minutes to be the time of concentration. So what governs is the larger of the contributing times. So we go down to our table, 10-year storm, 30-minute duration, 2.98 inches per hour. The peak flow rate would be intensity times the sum of the CA. So there's going to be a total of 8.60 feet per second through there. You can see the required diameter would be 1.7, which works out to 20 inches. The closest one we have is a 24-inch pipe. So if we've got a 24-inch pipe, then that means that the velocity of flow is going to be 2.74. We're getting closer to that lower limit of 2. And the travel time through that pipe would be 3.65 minutes. All right, 1:52. I actually kept you 2 minutes late. I'll give you back that 2 minutes, I promise. But I wanted to show you that design example. That's how we can do it manually. On Monday, the recorded video there is going to get into how we do this with Stormcat. So it's an automated way to avoid having to do it, setting up all the formulas manually. So look for that video for Monday, and then we'll be back together face-to-face in class on Wednesday.